Somewhere beneath 40 kilometers of ice, in an ocean that shouldn't exist, something is happening. We don't know exactly what. But what we've found suggests that, for the first time in human history, we may be looking at a place that is actively trying to produce life right now. This is Enceladus, and what scientists have uncovered here in the last 18 months has quietly changed everything. In 1789, William Herschel built the largest telescope the world had ever seen. Its bronze mirror weighed half a ton and took more than a year to hand polish. Through it, he discovered a tiny moon-orbiting Saturn, unremarkable, featureless, forgotten. For nearly 2 centuries, that was the whole story of Enceladus. Then, in 1981, the Voyager probe swept past Saturn in a matter of hours. The images it sent back didn't match the dead, cratered world everyone expected. Huge stretches of Enceladus were suspiciously smooth, geologically young, and stranger still, the moon sat right in the thickest part of Saturn's glowing E-ring. Something was feeding that ring from inside, but no one could explain how. On a moon this small, this far from the sun, there was no conceivable heat source. The science simply didn't add up. And so Enceladus became the most confusing object in the solar system, a question no one could answer. That question launched one of the most expensive and ambitious space missions ever attempted. The Cassini probe launched in 1997, carrying instruments designed to unravel Saturn's secrets. 7 years and 4 billion kilometers later, it entered Saturn's orbit. And in February 2005, it flew past Enceladus for the first time. What its cameras captured stopped NASA scientists cold. Erupting from the South Pole, not one, not two, but over 100 jets of water vapor and ice, blasting into space at 1,400 kilometers per hour. Each second, 250 kilograms of material were being hurled hundreds of kilometers above the surface. Enceladus wasn't a dead rock. It was erupting. The room where mission scientists were watching the data come in reportedly went completely silent. Then, one by one, everyone started grinning. Because if there was that much water escaping into space, the implication was staggering. There had to be a liquid ocean underneath. NASA immediately did something almost unheard of mid-mission. They rerouted Cassini. Instead of observing from a safe distance, they ordered the spacecraft, traveling at tens of thousands of kilometers per hour, to dive directly through the plumes. 50 kilometers from the surface. It was, by any engineering standard, reckless. The probe had not been designed for this. One wrong calculation, and a $3.9 billion spacecraft becomes debris. But the potential payoff was too enormous to ignore. What they might find in those plumes could answer the oldest question humanity has ever asked. Scientists hunting for life elsewhere in the universe use a 4-part checklist: liquid water, energy, the right chemistry, and time. Here's what we know. Water, not just a puddle. Enceladus has a global ocean, confirmed, wrapping the entire rocky core from pole to pole beneath an icy crust. Scientists figured this out not by drilling down, but by watching the moon wobble Enceladus rocks back and forth slightly more than it could if its core was locked to its surface. The only explanation, a liquid layer separating them. And in 2025, researchers analyzing archived Cassini infrared data made it stranger still. The North Pole, which should be frozen solid, is running 7 degrees warmer than any model predicted. Enceladus is generating far more internal heat than anyone realized. Energy. This is where it gets wild. The moon is tidally locked to Saturn, always showing the same face to the planet. Saturn's gravity constantly kneads and flexes the interior, and friction from that generates heat. That heat rises through the silicate rock core in focused hydrothermal plumes, warming the ocean from below. Hydrothermal vents. On Earth, these vents are where many scientists believe life first ignited, in the pitch-black deep ocean 3.5 billion years ago. Chemical reactions powered by heat, producing the first self-replicating molecules. Enceladus has the same setup in miniature, orbiting a gas giant 1,400 million kilometers from the Sun. Chemistry. Cassini's mass spectrometer, an instrument that identifies molecules by their chemical fingerprint, flew through the plumes and came back with a shopping list. Hydrogen, methane, carbon dioxide, complex hydrocarbons, nitrogen compounds, and in 2022, the final ingredient that completed the picture, phosphorus. All 6 elements scientists believe are essential for life: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur were present. But it gets better. Here's a problem no one expected. When Cassini flew through the plumes at 64,000 kilometers per hour, the mass spectrometer was essentially firing molecules at a detector at extreme speed. The impact shattered them, and a shattered molecule looks different from an intact one. Imagine trying to identify a watermelon after it's been hit by a truck. You'd have seeds, rind, red pulp, but you might not immediately know what you were looking at. That was the problem scientists faced for a decade. And then, last year, a team at the Institute of Space Systems in Stuttgart cracked it. Led by Nozer Khawaja, they developed analytical models that worked backward, understanding exactly how Cassini's detector had broken molecules apart, then reconstructing what those molecules looked like before impact. What they found in the plume data was unlike anything retrieved from space before. Cyclic esters, ethers, aldehydes, oxygen-bearing nitrogen compounds, alkenes, and alkanes. These aren't just building blocks. These are the molecular tool sets from which, in laboratory settings, researchers have watched chemistry spontaneously organize into increasingly complex structures. Structures capable of information storage, self-replication, and what scientists carefully call pre-Darwinian evolution. In plain language, with these same molecules, in lab conditions, chemistry starts behaving like the early stages of life. And the most pristine samples, collected when Cassini passed just 20 kilometers above the surface, before solar radiation could alter them, showed the highest concentration of complex organics ever detected beyond Earth. Then came the image that made scientists' jaws drop. The James Webb Space Telescope pointed at Enceladus and captured something Cassini had never seen at this scale. The plume erupting from the South Pole was so large it extended 20 times the diameter of the moon itself. Let that land. The moon is 500 kilometers across. The water plume above it stretched 10,000 kilometers into space. That plume is feeding a vast ring of water ice encircling Saturn, and it's been doing it long enough to affect the planet's atmospheric chemistry. Enceladus is the only known moon in the solar system that chemically alters its host planet's atmosphere from hundreds of thousands of kilometers away. It also creates something no one predicted: plasma waves 500,000 kilometers long called Alfvén wings, streaming from Enceladus to Saturn like a cosmic electrical circuit. This tiny moon is electrically connected to a planet 30 times its diameter, and we still don't fully understand what that means. Here's the part of this story that keeps scientists awake at night. In 2017, an amateur astronomer named Ted Strike was browsing old Voyager images, the same 1981 flybys that first revealed Enceladus's smooth surface. He was doing this on his own time, out of curiosity, on a personal computer. He found a plume, faint on the limb of the moon, but there. The plumes had been present in 1981, hiding inside data that had been publicly available for 36 years, that thousands of scientists had reviewed. No one saw it because no one was looking for it. This is what makes the search for life so humbling. Discovery isn't just about building better telescopes. It's about learning to see what we haven't yet imagined looking for. Several missions are being planned to go back. One proposes landing. One wants to analyze plume chemistry in far greater detail than Cassini could manage. But one mission defies easy description. The Enceladus Explorer, funded by the German Aerospace Center, proposes sending a nuclear-powered ice mole to the surface. A self-heating probe that would melt its way through 40 kilometers of ice, traveling slowly downward over months, sealing the tunnel behind it until it reaches the ocean. Then it releases a submersible to swim in an alien sea, searching for microbes. If that works, if we find even a single cell, even a fragment of biological chemistry, it would be the most important discovery in the history of science. Not one of, the most important. Every philosophy, every religion, every assumption about humanity's place in the universe would shift overnight. There's a line from physicist Jeremy England that I keep coming back to. He says life isn't a miracle, it's a tendency. Given the right ingredients and enough energy flowing through a system, matter has a tendency to organize, to self-replicate, to evolve. If he's right, then Enceladus, with its hidden ocean, its hydrothermal vents, its complex organics, its billions of years of geologic stability, isn't just a candidate for life. It might be a place where life was essentially inevitable. We don't know yet. We haven't gone back. But we're going. And when we do, we won't just be exploring a moon. We'll be confronting the question of whether life is a cosmic accident, or whether the universe has been quietly building it in the dark, all along. I want to know what you think. If we send that nuclear ice mole down through the crust and find microbes swimming in that ocean, what changes for you? Your worldview, your beliefs, your sense of what matters? Tell me in the comments. And if this kind of deep space storytelling is why you're here, subscribe. We're just getting started.